All right. This section is exciting for me. This is a cool section. All right. Diagonalization. So we just did characteristic equation or characteristic polynomial. Now it's time to jump in. In many cases, the eigenvalue, eigenvector information contained within a matrix A can be displayed in a useful factorization of the form A is equal to P D P inverse, where D is a diagonal matrix. In this section, the factorization enables us to compute powers of A quickly for large values of K. A fundamental idea in several applications of linear algebra. Later in section 5.6 and 7, the factorization will be used to analyze and decouple dynamical systems. The following example illustrates that powers of a diagonal matrix are easy to compute. Okay, so yeah, so this is pretty simple. Is you basically just power the elements. You don't even have to do much else, or you don't do anything else. Okay, so here they give you, they give you P and D, and they tell you that A is equal to P, D, P inverse. So then you find P inverse, and then you just start computing powers of D, and then you compute this thing, and then it gives you A to the K. So it's actually pretty fast. A square matrix A is said to be diagonalizable if A is similar to a diagonal matrix. That is, A equals PDP inverse for some invertible matrix P and some diagonal matrix D. The next theorem gives a characterization of diagonal matrices and tells us how to construct a suitable factorization. Theorem 5, the diagonalization theorem. An n by n matrix A is diagonalizable if and only if A has n linearly independent eigenvectors. Oh, that's so cool. Is that for real, man? That's so cool. In fact, A equals PDP inverse with a diagonal matrix if and only if the columns of P are linearly independent eigenvectors of A. Wait, really? The columns of P are linearly independent, are the linearly independent vectors of A. In this case, the diagonal entries of D are eigenvalues. Oh, really? Whoa, you're blowing my mind here, Chief Tan. That's crazy. A is diagonalizable if and only if there are enough eigenvectors to form a basis of Rn. We call such a basis an eigenvector basis of Rn. First, the proof. First, observe that if P is any n by n matrix with columns v1 to vn, and D is any diagonal matrix with diagonal entries lambda 1 to lambda n, then A times P is equal to the n matrix vector products of A with the columns of P, okay? And PD is equal to P times that, which is just going to be yeah. Okay, so I see that. Now suppose that A is diagonalizable and A is equal to PDP inverse. Then multiplying this relation by P, we have AP is equal to PD. In this case, equations 1 and 2 imply equating columns. We find that, yeah, okay, so, oh wow. Since P is invertible, its columns must be linearly independent. Also, since these columns are non-zero, the equations in 4 show that lambda 1 and to lambda n are eigenvalues of, and v1 to vn are the corresponding eigenvectors. This proves the only if parts of the first and second statements along with the third statement. Yeah. Now suppose A is diagonalizable. That's a very exciting theorem. That's so cool. Well, what does diagonalizable mean? It means similar to a. Means similar to a diagonal. It doesn't actually mean that you. It doesn't mean that an equivalent linear transformation. Well, does it? Is there Surely there's a Actually, I think it might be on here. The determinant inverses, dot products, cross products, Cramer's rule, change of basis. Interestingly, there's no video on diagonalization. Okay. You kind of would think that he would have one. I.e. A is equal to P dP inverse. So the theorem 5, is A n by n diagable if and only if A has n lin independent eigenvectors. So if you got n So if we took, for instance, okay, yeah. What's up, happy time, Larry the Lobster Man? Okay, so how do you answer a question like that? The Okay, so we're at a point at linear algebra where you do need a little bit of background, but I'll try to give a quick explanation of what it is that we're learning. So linear algebra is the study of the spaces called vector spaces and the transformations between vector spaces. That's kind of abstract, but you can think of like the plane, like you're the standard plane that you get in when you're plotting graphs in elementary school, and the plane forms a vector space where the set of arrows from the origin, or equivalently, you could think of it as the set of points in the plane, form the elements of the plane. And the main thing you need to know about a vector space really is that you can add two vectors and you can scale a vector by some amount. So you can take an arrow and you can make it longer or shorter, but keep it pointing in the same direction. So that's sort of like what vector spaces are all about. And linear transformations, which are the maps between vector spaces, or what you call them, are the easiest way to think of them is as a matrix multiplication, or as multiplying a vector by a matrix of numbers. And it turns out that you can view these transformations in all sorts of really cool ways. It's like a linear combination of the columns of the matrix, but the most important part for what we're doing now is that those matrix vector multiplications, basically the multiplication of a matrix with a vector, there are certain vectors by which they don't change their direction at all, even when multiplied by that matrix. They only get scaled. And so those vectors have a special name called eigenvectors, which is a German word. And the amount they get scaled by is called an eigenvalue. And what we're learning now is that if you have n linearly independent eigenvectors, which you need to know the definition of linearly independent, but basically linearly independent means if you have two arrows, there's no way to scale one of the arrows so that it equals the other one. So like if they're pointing in different directions, there's no way to really change one of them into the other without like fundamentally messing with it. So that's what linearly independent means. And that's only for two vectors. It gets slightly more complicated when you have more than two vectors, because you basically, when you have more than two vectors, linearly independent means there's no way to scale and add the other vectors together such that it equals the first one. But anyways, let's move on, because we need to do my homework at some point. But that's the fundamental gist of linear algebra and bringing you up to speed with the diagonalization theorem. So the theorem is okay, so that means that eigenvectors of A span Rn. And what that means is we call it an eigenvector basis. A basis is just a set of vectors where you can reach any point in your plane with the smallest number of vectors possible. Okay, the proof is just observe that, A times some, okay, so P is n by n with, equal to V1 ... Vn, and D is diagonal with lambda 1 to lambda n. Okay. The proof of the diagonalizable. I'm just gonna write the proof sketch out so that I have it in my head. So just note A times P is equal to A times v1 to vn is equal to av1 to avn. All right. Oh, thanks, man. Yeah, you know, the thing about this is it gets so much less complicated when you just do problems. Like when you just do the homework, it starts to become so much easier. I wish I had known that. Like, so, like, I don't know. I wish I had appreciated that, you know, because I'm going to level with you. I don't think you can really learn too much from videos. I think you can be inspired and you can, like, get the idea, but I don't think you can really learn it just by watching. I think the only way to really get it is to do it. Okay, so yeah, so then we have, hold on. Now suppose A is diagonalizable. Okay, so we're doing this side of the proof. So we assume that A is equal to PDP inverse. And we're trying to show that it has, then we're going to try to show then you right multiply by P inverse and you get, oh no, you right multiply this relation by P, you get AP equals PD. And then you find the, yeah, okay, so then this shows, since P is invertible, its columns must be linearly independent. Okay. Okay, so that's the proof this way. So, but did we assume that? Well, we assume that it's diagonalizable, and the definition of diagonalizable is that there exists some invertible P. Okay, but that's fine. Finally, given n eigenvectors and use them to construct the columns of P. Okay, yeah. So we get this. All right. So diagonalizing. Okay. So how do you actually find the diagonal? How do you find the P in the? No. We know how to construct it. You just find the eigenvalues and the eigenvectors. There are 4 steps. Find the eigenvalues, find the eigenvectors, make P, make D. That's so easy. Diagonalize the following matrix. Okay, we did it. Yeah, so this is sufficient but not necessary. Because you could have... Because just think of the identity matrix. The identity matrix is diagonal already. But it doesn't have n distinct eigenvalues. So, well, let's see what the proof of this is. Let v1 to vn be eigenvectors corresponding to the n distinct eigenvalues of a matrix A. Then v1 to vn is linearly independent by theorem 2 of section 1. Okay, so that was actually really easy. It is not necessary for them to be distinct. This is not diagonalizable because one of the eigenvalues is 0. Oh, wait. Oh, wow, that's actually... No, I'm wrong. Why did I think that? It's not... you can't invert it. This is no inverse, but it is diagonalizable. Wow, okay. This is a good example, actually. So I'm just gonna write that down. So 5, 8, minus 8, 1, 0, 0, 7, 0, 0, minus 2 is diagonal, even though it's not invertible. Invertible. So what's it called when it's invertible and... What's it called when a matrix is invertible and diagonalizable? I wonder if can I do diagonal? If I do this 1, 2, 3, does this work? What the hell? Oh, I think I have to do this. M. What? How do you make a diagonal matrix? Oh, you know what I think I have to do? Actually, what about this? I think this might work. There you go. But the thing is, if I compute inv of A, oh, but the inverse of a diagonal matrix is diagonal. Yeah. Oh, and in fact, it's actually the inverse of the elements themselves. Right, that actually makes sense. That's obvious. I don't know what I'm doing. I'm just fucking around, man. I don't even know what I'm talking about. Matrices whose eigenvalues are not distinct. If an n by n matrix has n distinct eigenvalues with corresponding v1 to vn eigenvectors, and if p, then p is automatically invertible because its columns are linearly independent. When A is diagonalizable but has fewer than n distinct eigenvalues, it is still possible to build P in a way that makes P automatically invertible. Oh, that's actually kind of interesting. I mean, the easiest way to think about all this is like the identity matrix clearly has all the nice properties that you want. It's invertible, it's diagonalizable, whatever. So, but it doesn't have distinct eigenvalues. So, you know, it kind of gives you that. Let A be an n by n matrix whose distinct eigenvalues are lambda 1 and lambda p. For k in between 1 to p, the dimension of the eigenspace for lambda k is less than or equal to the multiplicity of the... Yeah. The dimension of the eigenspace for lambda k is less than or equal to the multiplicity of the eigenvalue lambda k. Trying to think about that. The matrix A is diagonalizable if and only if the sum of the dimensions of the eigenspace equals n. That's... Oh, yeah, that's interesting. So this is a little bit of a generalization because I was sort of implicitly assuming that if they're distinct, then you actually get all multiplicity ones. Okay, yeah. So the characteristic polynomial completely factors into linear factors. And 2, the dimension of the eigenspace for each lambda k equals the multiplicity of lambda k. If A is diagonal and bk is a basis for the eigenspace corresponding to lambda k, then the total collection of vectors b1 to bp but the thing here that you have to note is that these bases are not just vectors. Five, 5, minus 3, minus 3. Since A is triangular, the diagonal are the things, and they both have multiplicity 2. Using the method in section 5.1, we find a basis for each eigenspace. And the way you do that is you just compute the null space of A minus 5 lambda, or 5I. Okay, so the set V1 to V4 is linearly independent by theorem 7. Yeah, because, okay. So the matrix P, so all you really need to know is that the sum of the dimensional eigenspaces is equal to n. If you know that, then you're good. Cool. All right, that's not that bad. Compute A to the 8, where A is 4 minus 3, 2 minus 1. We can just I don't even really want to do that, but we could do that. Actually, I wonder if internally, if you take like I'm curious to see how much faster it is. It should be way faster because the matrix multiplication's n cubed, but to compute a power of the diagonal, because I guess testing whether a matrix is diagonalizable is already repeated squaring. Oh, repeated squaring. That's smart, actually. Repeated squaring is smart. I didn't think about that. If you recurse on that, then you get a log. Yeah, that's good. That's smart, man. But you can still do that here, too. You can get a log in there, too. Wait, hold on. Yeah, so that's going to be 2n cubed. I mean, this is pretty big, though. N cubed log m. Yeah, right. So you remove the log m. And you and the log savings on D of m, it doesn't even matter. It's like you're talking about log n. Like when you're talking about n cubed compared to log m rather. Yeah, but that's whatever. I don't even freaking care. I don't even freaking care about that. No, I am not a grad student. This is linear algebra, bro. But I am old though. I'm just kind of getting into this after a long time of taking a break, really. But it's exciting. It's really cool. I'm in differential equations too. And differential equations in linear algebra have some really cool synergy. They have some really cool connections to each other. Like linear differential equations, pretty neat stuff. All right. So this you do the thing. Wait, but actually is there a method called diagonalize? How to Because I'm pretty sure what you can do is you can just do, like if we have this, we can just do, let's say E is equal to eigen of A. Then we can do uh, P equals E dot vectors and D equals diagonal of E dot values. And then you can just do P times, yeah, so there's the identity. There really isn't any other way to do that. You would expect that there would be a one, let's just see. I would expect there would be like a one line. Do you have to use eigensystem too? Interesting. Okay, so I guess I guess people don't really do this in practice because it's not easy. Where are we going? All right, so let's look at this stuff. Usually I like to skip these because yeah, okay, compute a to the 4. I don't care about that. Put it into this form, this form. It's all computation. Let's do the true false though. A, P, and D are n by n. All right, 21. A is diagonalizable if it's no. See that's false. Because otherwise, that the name diagonalizable would be totally misnomer. So 21 is false because it doesn't specify that D is diagonalizable. If Rn has a basis of eigenvectors of A, then A is diagonalizable. That's true. A is diagonalizable if and only if A has n eigenvalues. That one's interesting. I think that that's actually true. Wait, because what if we consider, like, let's say, ones 3 by 3. Oops. But then we did upper. How do you do this? Upper triangular. Okay, but then ugh. I mean, it has. Wait, no, but you what? But that's not what I'm actually trying to say. I'm trying to say, like one, one. Wait, 1, 1, 1. 0, 0, 1, 0, 0, 0. Um, because doesn't every matrix have uh because I thought it seems like yeah, right. Over an algebraically closed field. So um but what's an example of something that's not diagonalizable? Maybe is the question. So that would be something where you have linearly dependent eigenvectors. Because that's I th- oh, okay, yeah. Okay, that makes sense. So that's false. If A is diagonalizable, then A is invertible. That's false. But what's an example? Wait, if A is diagonalizable, then it's invertible. Actually, that might be true. If A is diagonalizable, then it's invertible. No, no, that's not true because you can have a zero eigenvalue. Because you can have a zero eigenvalue and be diagonalizable, as we saw in this example. So it's not even that. Okay, so that's 24 is false. 25 is also false. They're just trying to trick you because it didn't say independent. But what's a case where we have a what's a case Wait, no, wait. This seems almost certainly false because yeah. Okay, so that makes sense. Okay. Wait, so 26. If A is diagonalizable, then it has n distinct eigenvalues. That's false. 27. If AP equals PD with D diagonal, then the non-zero columns of P must be the eigenvectors of A. This is a good one because I don't know. Because you want them to be invertible, and I'm just wondering if, given the information, we know that it's invertible. I'm gonna say false, but I actually think it could be true. It's so windy. And then 28, if it's invertible, '28. I really want to know. I actually don't know. This is the first time that I've been like I don't even know. 28. I don't know. It's invertible. Wait. right? 21 didn't say that. It just said for some matrix D. Okay. So that's okay. So GPT got that one wrong. 22. True. 23. Okay. 24. False. Yeah. Yeah. 25. False. Okay. 26. False. Yeah, that one was easy. 27. They said true. But I'm trying to think because 28. Oh wow. Yeah, I didn't think about that. The Jordan block is actually one of the best test matrices. Oh, okay. So then this one's so that one, which one was it? 27 is true. Okay, good. Okay, let's try to bang these out, and then we're gonna end the stream, and then I'm gonna do a bunch of types document setting because I have a homework to do tonight. A is 5 by 5 with 2 eigenvalues. Ooh, that's a good question, man. 29. If A is a 5 by 5 matrix with 2 eigenvalues, one eigenspace is 3-dimensional and the other is 2, is A diagonalizable? Is it possible there's overlap is my question. We need an example. Is it possible that there's overlap? I'm actually kind of leaning towards no, just because I can construct subspaces that I can construct 2 subspaces, one that's 2-dimensional, one that's 3-dimensional, but whose what is it called? Direct sum is 4-dimensional, meaning less than 5-dimensional. So, but I don't know if that's possible with the structure of eigenvalues. So we need to think about that. I'm almost certain this is false, because if we consider two rows that are like scalar multiples of each other, let me do, like, if we did like that's not what I was expecting. That's not what I was expecting at all, actually. It's wild. Um, Damn, I really am going back and forth. Let's ask ChatGPT. I really want to know this one. How do we know the eigenspaces don't overlap? Is the wait? Wow. Okay. Yeah. Geometry. That actually makes sense. That's really cool. I still don't exactly see geometrically why that's the case, but that's cool. 29 is yes. A is a 3x3 matrix with 2 eigenvalues. Each eigenspace is one-dimensional. No, because it's not diagonalizable because, well, first off, is this even possible? How is this possible? I guess this is over the reals. I'm pretty sure that this is only... Yeah, because I don't think that you can get some water. Two 1 0 0 2 0 0 0 3. Oh, cool, bro. I didn't see this. Yeah, man. That sucks, dude. Bro, community college actually kind of rules. That's good for you, man. I'm in community college right now too. Honestly, it's like cheap compared to these freaking private schools, bro. It's cheap, and I mean, you're not gonna get the best professors, but like if you have the skills to teach yourself, and ChatGPT, pretty good. I actually recommend it. I'm doing that too. What is it? 210-020-003. Right. So even though you can have um an eigenval with algebraic multiplicity to the um eigenspace can still be 1D. Okay. I'm going to say no, right? Because we know that there is another eigenvalue. And I'm pretty sure that it said that, for any. I mean, does this mean they're distinct? I don't know. If they're distinct, I would say yes, for sure. Or I would say it is not possible. So it does. So these are the subspaces with one-dimensional. Man, I'm getting tired. I can't see why. I can't see it. I need more visuals, dude. I need more visuals. All right. These are good problems, though. Yes, it is. Because it's possible that the... Yeah, you could think of it like 1, 1. You could think of it like, maybe it's like, on the diagonal, it's like, 1, 2, 2, 3. But in this case with 7. Okay, so, all right, A is both diagonalizable and invertible. So that means that A equals P, D, P inverse, with P invertible and D diagonal. So now we need to show that A inverse equals P, I don't know, we'll say P1 or P2, D2, P inverse 2. I think you just invert. D. I think because D is diagonal and diagonal. Actually, diagonal doesn't imply invertible. So maybe I can't do this. Okay, we gotta end this soon, man. I'm getting tired. Thanks, man. Cool, bro. That's awesome, dude. It's so nice to hear from you, bro. Since A is invertible, none of the diagonal entries can be 0. Oh, yeah, that's true. No, that's not. Yeah, all right, cool. So we were right. So I got it. Yeah, you just do that. Nice. Okay, that's actually going to be it for me. All right, cool. All right, peace out, bro.